Okay, so welcome to this week. So till now we have basically got an idea of how operating systems work. And I hope that by now you have got a decent idea of an important mechanism called system calls. Right? So we discussed that system calls are that mechanism by which application programs can ask for some service from the operating system or from, on a more, if I want to use a more technical term, system call is the mechanism by which application programs can ask for some service from the kernel. Right? So we will continue to use the word kernel and operating system in a kind of interchangeable way, but we know that kernel is some fundamental building blocks of the OS. So what are system calls? Basically, we have discussed this and we have also seen this kind of a picture. So it is the mechanism used by an application program to request service from the operating system or kernel. Right? So we have seen this kind of a picture. So suppose a user process or application is executing, and we also discussed that there are two modes of working for a CPU, the user mode and the kernel mode. And there is a hardware mode bit in the CPU which tells the CPU in which mode it is working. Right? So when user process is executing, the CPU is in user mode. Then suppose this user process makes a system call, like a printf or scanf or something like that, where it cannot do it directly, it needs kernel support. So then the mode bit, so basically some kernel subroutine starts being called. This is exactly what we will discuss today, how this happens. So some kernel function or some kernel subroutine starts being executed and the mode bit changes to 0. Then that kernel function executes the system call, and then when it returns, it sets the mode bit to 1, and then again the CPU comes back to user mode and is running with the user process. Okay. Okay, guys, give me 1 minute. Sorry, give me just 1 minute. Yeah, hello. Sorry for the interruption. Okay. So yeah, so this thing we have discussed, and so in this lecture we are going to get into a bit more detail about how this actually happens. So a user process is executing, it has made a system call, now some kernel function will start running. So how does that happen? So basically we will check how system calls work, and we will see that system calls actually have a important relationship with interrupts. Now, since all of you have done a computer organization architecture course, I assume that you have a fairly good knowledge about interrupts. Right, so we will do a small overview. However, we expect that you know how interrupts work. So as we will see, system calls also have a very big relationship with interrupts, right? And actually, in earlier days, the system calls used to be handled quite similar to interrupts, right? So let us check that. Okay. So in earlier days, as I said, system calls used a very similar mechanism as interrupts. So there used to be an instruction called int, right? And that was used to raise an interrupt. And therefore system calls also use this mechanism. So to get a better idea, let us briefly see how interrupts work. This part will mostly be a recap of what you have learned in Goa. Still, let's do a small recap. So a processor usually provides several interrupts, right? And broadly, there are two types of interrupts provided by a processor usually. Some interrupts are called synchronous. They will happen every time an instruction executes with a given program state. So for example, in your program, let's say by some mistake you have got a divide operation, and by some mistake the denominator value is 0. So whenever this happens, an interrupt will be raised. Or you are making a bad pointer dereference. Sometimes we forget to give the ampersand in scanf or something like that. So that is a bad pointer dereference. So clearly your program is trying to do something which it should not do. In such cases, there is a interrupt. Or maybe the application wants some service or syscall. So in all these cases, an interrupt can be raised. These interrupts are called synchronous. That means you know that this will happen, as in if okay. Just one point. Usually we use the word synchronous with respect to time, but here the discussion is not exactly with respect to time. It's basically that whether you know kind of that as this, I mean, when this instruction will be executed, whether there will be an interrupt. Right. So the synchronous interrupts, they occur because of some specific event which is happening inside the CPU itself. That's why they are called synchronous. The other type of interrupts provided by a processor are called asynchronous. This is usually caused by an external event, means external to the CPU. For example, the IO device or the timer, they interrupt the CPU. Okay. So maybe an IO device has to signal the CPU when an IO process is done. Maybe an IO process was started by the CPU. So then the device must inform the CPU that yes, now this IO operation is completed. So then that IO device can raise an interrupt. Right, so the distinction is that the synchronous the synchronous interrupts are happening as a result of some event happening inside the CPU, you might say. And the asynchronous interrupts are happening due to some external event. So the CPU has no way of knowing when that asynchronous interrupt will come. So there are broadly these two types of interrupts, and some CPUs have given specific names to these two types of interrupts. For example, Intel used these two terms for these two types of interrupts. The synchronous interrupts were called exceptions, and the asynchronous ones were actually called interrupts. Okay, so these are just two terms that Intel used. Other CPUs did not use similar terms. Maybe they use something else, but essentially the concept is synchronous and asynchronous interrupts. Intel used these two terms, exceptions and interrupts. However, importantly, from the programmer's perspective, both exceptions and interrupts were handled with the same abstractions. So essentially, say at a high level, suppose an exception has happened or an interrupt has happened, but whatever it is, the current user application which is running will have to be postponed, as in will have to be swapped out, what we say, and the CPU will have to be allocated to a kernel subroutine or a kernel function. Right, so from a programmer's perspective, the abstraction remains the same, whether it has been an exception or an interrupt. But maybe internally the CPU distinguishes between these two. Okay. So how do interrupts work? We are continuing the recap. So essentially, each interrupt or exception has a number indicating its type. Say typically, say 14 was a page fault. Right? Now, suppose a page fault has occurred, some interrupt has come. So again, understand that the CPU basically does this throughout its life. As long as it is switched on, the CPU will do this. It will take the next instruction from the program counter and will execute it. Right? So somewhere it needs to be known, the CPU needs to know from where to fetch the next instruction. The CPU, understand this very carefully, at any point of time, the CPU needs to know from where to fetch the next instruction. So things that when we are telling things like, so we often make statements like this. So the user program is executing, an interrupt has come. Now a kernel routine will start and handle that interrupt. So the question is exactly how will this happen? So for this to happen, the CPU needs to know which kernel routine to start. Right? So the kernel routine is also somewhere in memory, but that instruction, the starting point of that kernel routine, that should be loaded onto the CPU. Right? The CPU should find out or should know or should have a mechanism to know that which kernel routine should I start. Right? So for this is how it used to be handled. Kernel created an array of interrupt descriptors in memory called the interrupt descriptor table, in short IDT. And this number here, as I said, every instruction, every interrupt or exception has a number. This number is actually an index into the IDT. Right. So now the IDT can be anywhere in the memory and it is pointed to by a special register, the IDTR. So at any point of time, the CPU can figure out where IDT starts because the start of the IDT is in a special register. The picture is something like this. Okay. So this is just like a pictorial representation of the x86 interrupt table. So this is the IDT where somewhere in memory, and I mean in Intel, I mean at a certain point, till a certain point of time at least, Intel processors used to define 255 interrupts. Okay, so this is the IDT somewhere in the memory, and there is this special register called IDTR, which points to the starting address of the interrupt table. And these numbers are the interrupt numbers. And what does this IDT contain? The answer is this. The IDT entry J specifies things like what code to execute for interrupt J. So basically the starting address of the interrupt handler or the privilege level necessary to raise the interrupt. So for example, page fault, like a user program cannot raise this interrupt for page fault. And user program can raise other interrupts. Right? There were several software configurable interrupts. That's separate. But a page fault is typically an interrupt which a user program cannot raise. Right? So even to raise a page fault interrupt, a certain privilege level is needed. So maybe all those bookkeeping used to be done using this IDT entry. So essentially IDT entry J specified what code to execute for interrupt J. A quick question. Does this make sense? Like from what you know about C programming, etc. Does this make sense that how can a table entry specify what code to execute? So a table entry is logically like an array. It may be a linked list kind of thing, but logically it's an array. How can an array element specify what code to execute? Exactly. So Shubham has given the answer. There is something called function pointer. Right. So if you are not familiar with it, I would suggest you to read any good C programming book, like say Carnegie and Ritchie or something. But essentially there is a concept called function pointer. So just like we have pointers to variables, we can also have pointers to functions. Basically, a function pointer gives the starting address of the first instruction of that function, or from where should execution of that function start. So using that kind of a concept, the interrupt handler is a function. So the starting address of the interrupt handler is loaded in this IDT entry J. So basically, suppose interrupt 14 comes, the CPU knows where the IDT is because its IDT is in the memory, but where it is in the memory is pointed to by this IDTR. So the CPU knows that, and it can figure out the 14th, entry number 14 of this IDT, and there it will find what code to run for this interrupt. Okay, so this is how interrupts used to work. Also, as I said, page fault is a hardware interrupt. There were also software interrupts. So there was this special instruction called int. So int num, where this would be a number. This instruction could be used by a software program to raise an interrupt. So what happens when a program issues int num? Control jumps to the kernel at a prescribed address, which is the address of the interrupt handler. And how will the say the kernel know? How will this address be filled into the CPU? Using this IDT. So as I said, IDT, there is a register holding the starting address of IDT, and using that it knows what the size of every entry of IDT is. So it can figure out the entry number num, right? So entry with index num in the IDT, it can figure out, and that is the next instruction address. So that is the interrupt handler within the kernel. So it should run. Okay. Now, before even running that interrupt handler, something needs to be done. What is that? The program which was running till now, that needs to be saved, right? Because it has to be resumed later. So this is an important step. The register state of that program, of the current program, I mean the program which was running till now, is saved by the kernel. So even before the interrupt handler starts running, the register state of the program which was running till now is saved by the kernel. Then interrupt handler runs and handles the interrupt, and when handler completes, this program which was running, which had raised this int instruction, that is resumed. Okay. Now here is something which I guess all of you know this, still I would like to emphasize. This is a very important step. So in all these time sharing systems or multitasking systems, we often say that one program is running, something happens, maybe that program itself makes a system call or some interrupt comes, etc. So temporarily the CPU is deallocated from this program. Some other program runs. Later at some point, this program will again be allocated to CPU. Right? So we often are making these statements, which seems that one program is running for some time. Then for a certain amount of time, it will be deallocated from the CPU. Again, later this program will resume and so on. Right? So this is an important step. And how is this done? Basically, by saving the register state of a program. Right. So again, understand this. We are talking about things like pause and resume. Right. So all of us see videos on YouTube and all. You see, you have pause and resume buttons. When you pause, the video stops, but it is remembered at till what point the video was seen, and then you can resume later. We are doing something similar for processors. Right. So a process was running till now. We pause it. The CPU is allocated to some other process. At a later point of time, we will resume this process. Right. By the way, so how is it done? How is it done? This is the answer. The register state of the program is saved. Right. So this is an important concept for which we have a separate, it is so important that we have a separate slide for that. So the particular state that a program is in now is succinctly and completely represented by the CPU register state. Right. So if you think what state is a program in now, the answer is the CPU register state. All the CPU registers, whatever value this program has stored in the CPU registers, that represents its state. So if you want to pause a program so that some other program can be allocated to the CPU, what you simply need to do is so the kernel needs to dump the register contents into the memory. And what you need to do to resume the program, just reading the register contents back from the memory to the CPU. So this is all that is needed to pause a program and resume a program. Okay. And this is done many times. Every time the CPU is deallocated from one program and allocated to another, this has to be done. I hope this point is clear, right? So now going back, as I said, this is how an interrupt is handled. The controller jumps to a kernel at a prescribed address. This is managed via the IDT. And that IDT first saves the register state of the current program. Then the interrupt handler runs, returns, and etc. and handles the interrupt. Then when handler completes, again, the kernel will decide which program to resume, and that saved state of that program will be loaded back into the CPU. Okay. Okay. Any questions till now? Yeah. So this was a brief recap of how interrupts work. Right, now we had started this class talking about system calls, but we possibly digressed a bit and discussed interrupts. But now we will join the loop, like why we were discussing interrupts. Okay, before that, a question. What would happen if programs are executed in a cyclic way? I did not understand the question. So Dhrumil, can you unmute yourself?
Hello, sir.
Yeah.
Sir, I mean, when we are executing program A, it makes an interrupt and then some program B is run and then there's another interrupt and then some program C is run and then there's another interrupt and the program A is run again. So
Yeah.
what would happen in that case?
So every program, when it raises an interrupt, will be deallocated from the CPU, and then that interrupt handler will run. So see, this is similar to how you call one function. So the main function may call one function, that function may call another function, and so on. So I think you know how these things are handled.
Sir, I mean, if the first function is called again, then won't it create like an infinite loop kind of thing?
Okay, that's a good point. Okay, first of all, it can happen. I think we all know about recursion, right? However, you are right that, okay, if that is what you mean, that's a good point. So that's a very good point. So actually there are some, so like these interrupt handlers, etc., they are not written in any normal, just like that, like in a rough way. They are written in a particular way such that this point is covered. That means suppose one program has asked for an input and that interrupt handler for inputs is running now. Right, now it can happen that within this some other, just a minute. What? Okay, Nikhil I think has a point to add here. If it happens every time a function is called, a part of it would be completed, so the process would be completed sometime. Yeah, so that is what I am also trying to say. First of all, suppose okay, I think there are both sides to this. One thing is the question which Rumil asked. So first of all, can it happen? The answer is yes, it can happen. As in one program asked for inputs. One program asked for input. So the interrupt handler or some kernel routine for handling input was running, but before it could complete, it was swapped out, etc. Another program which was currently in the CPU that also asked for input. It can happen. So first of all, one thing is this is not an uncommon situation. This happens, and therefore the kernel routines which are used for handling interrupts, etc., they have to be written in a particular way. I'm not going to discuss that in detail, but yes, they have to be written in a particular way. Any idea what that way is called? Like it's a way of writing code, as in, okay, I should not say a way of writing code, okay. A particular function, whether it has that property or not, that before one instance of that function is complete, another instance of that function can be called. Functions written in this way have a particular name. Any idea what that name is? Tail recursion? No, not quite. Okay. I am not sure about some of the terms that you were saying, like coroutine. I do not know, so I'm not commenting whether that is right or wrong. It may be that that's also right, but the term which I had in mind is this. Sometimes you will see this term, reentrant. Okay, so basically once control has entered a function, even before it is complete, control can again enter that function. Right. So some functions have to be written in this way with carefully using arrays, etc., or variables. These are usually called reentrant. So yes, so one part is that I'm not going into that much detail here, but yeah, these kernel routines which handle interrupts, etc., they must have some properties, one of which is this reentrant nature. So that's a good point which Dhumil asked. Okay. However, yes, what Nikhil also pointed out, that see, there is no need to think this is going on an infinite loop kind of thing, because at some point the operations will be completed, right? So suppose yes, multiple programs have asked for inputs. Okay. However, at some point, some of the inputs will be completed. So there is no need to think that there is infinite loop kind of thing which is happening, which will never complete. Right. So at some point, every function will complete its work. Like the input for a particular program, maybe 5 different programs have asked for inputs. So at a particular point of time, 5 different programs have asked for inputs. Now none of them are allocated to CPU because all of them are waiting for the inputs. But then the input routine of one program must be running now. So that will complete. Next, some other program's input routine will be complete and so on. Right. So the question of infinite loops, etc. does not come here. Okay, there are a couple of other questions I see. Tanmay is asking, when we dump the register values to memory, we need another register to hold the address of the memory where our register is dumped. Excellent question. So let me ask you, do you know what this is? So Tanmay is asking a very valid question. Say when kernel is dumping the register. Again, by the way, let me just point out, the question is very good, but try to form the questions a bit more technically. Like when we dump the register, who are we here? Right. So try to formulate the question a bit more technically, because if you do that, often you will get the answer itself. So here the kernel is dumping the register, right? So the kernel is dumping the register values of a particular program to memory. So then the kernel needs to figure out at which memory it will dump the register. It will dump the registers of that program. So the Tanmay is asking, is there another register which holds that at memory where the register, okay, it's getting confusing, wait. Program A is running. Kernel wants to dump the registers of A into memory. So kernel must know at which point in memory should registers of program A be dumped. So Tanmay is asking, is there another register where this memory location would be noted, where registers of program A would be dumped by the kernel? So my answer is yes, but I am asking you all. You should have some idea of what that there is this mechanism. What is that? Exactly. Pankaj and Shubham have given the right answer. Stack. Kernel has its own stack. Okay. Kernel has its own stack. It has its own stack pointer. And these things are being dumped in the stack itself. Right. So kernel is also like a program. Don't think kernel is like a miracle kind of thing. Kernel is also a program. So exactly how your program handles these things, kernel will also do the same thing. Kernel has its stack. That is, it has a stack pointer. Right. So kernel knows what to dump these say registers of particular programs, etc. It will just create another stack frame and dump the point. I mean, dump the of this process. Of course, kernel has to maintain several data structures, some of which we will see in the next few weeks. So, but yeah, I mean, the concept is similar to a stack. Though actually, yeah, I mean, conceptually a stack, but actually it's a bit different. It's more like a queue, right? So we will start talking about queues like later this week or next week. So the kernel maintains several queues of processes. So let's say the kernel uses a queue to remember which processes are waiting for the CPU, right? Kernel uses a queue to remember which processes are waiting for a particular event. So kernel uses these queues. So actually it is dumping there. But yeah, the concept is like similar to using a stack pointer kind of thing. So there is of course a register which tells the kernel where to dump the register values. Okay, another question by Rashil. At what point do we stop calling a normal functionality an interrupt? Like the YouTube pause. Okay, come on, see. The YouTube thing I gave purely as an analogy to explain pause and resume. YouTube has nothing to do with interrupts. Okay, so I'm sorry if these examples are confusing you, then possibly then maybe I'm making a mistake in giving these examples. But YouTube has nothing to do with system interrupts. That is just your browser is talking with the YouTube server and both are applications and you have decided to pause the video. So nothing, I mean, okay, so if that example has confused you, then I'm sorry, but I just used that example to explain about pausing and resuming. YouTube has nothing to do with interrupts. It's completely application level. Your browser is talking to another application running in the YouTube server, etc. Okay, now Tanmay has another question. The sole purpose of register is to eliminate the time taken to load the memory contents whenever an operation is performed on them. If we need to load the registers frequently, then what is the use of registers? Very good question. So you are right. So registers are much faster, etc. But then the question is, how many registers can you have in a CPU? A few hundred, maybe a few thousand. Nowadays, processors do have register files containing possibly a few thousand registers. But that's all. You cannot have an infinite number of registers. So therefore, if you say that, so at a particular point of time, you do not know how many programs will have to be, kept ready or how many programs will have to be dumped. So it's quite possible that like when a software lab is going on in the computer server, maybe 100 people are running 200 programs. So then do you think there will be 200 sets of registers to save each of them when necessary? Okay, it can be possible. But then at some point there can be 500 programs. So how many register sets can you give? Right. So of course it would have been much faster if registers could have been used to, keep to remember every state of every running program. But then you would need an infinite number of registers. And no CPU can provide that. Right. So CPUs can even provide thousands of registers, but not infinite. Therefore, of course, it is a overhead. Right. But there is no other way other than loading it into memory. And see, it's one good thing that you are noticing that this switching from one process to another, like deallocating the CPU from one process and allocating it to another process, this has an overhead. And that is why it is not desirable to do this too frequently. Remember, we talked about things like what's that called? CPU burst, IO burst, etc. So a CPU burst, the concept comes from this, that we do not want to do such switching very frequently. Therefore, once a process is allocated the CPU, it should try to do many CPU operations instead of just again requesting a context switch or requesting an IO operation, which will make another context switch. Okay. So yes, context switch is overhead. So this switching the CPU from one process to another is called context switch. We will discuss this term soon. But yes, this is overhead. But then there is no other way. You cannot handle everything using a fixed number of registers. Okay. Fine. Any other questions? Okay, let me proceed. Okay, so till now was a overview of how interrupts worked. I really think that this is not what we discussed till now is not new. Your COA course should have given you some ideas. But now let us talk about system calls. And the reason why we talked about interrupts is this, that originally in earlier days, system calls used to be handled the same way as interrupts. So system calls also used to be issued using the int instruction. And the system call handler routine was just another interrupt handler. Right. So earlier days, the system calls used to be very much handled similar to interrupts. And like interrupts, system calls used to be arranged in a table also, right? So basically, whenever a system call came, we use the term syscall as a short form of system call. Whenever a syscall came, interrupt driven in those days, the program selects which syscall it wants, right? And the way of doing it, handling it in hardware is you place the index in a particular register, index to this table. This, as I said, system calls also used a table similar to the IVT. So the index in that table is that which interrupt or which syscall the program wants. Say there is a syscall maybe for interrupt. Sorry, there is a syscall for inputs. There is another separate syscall for output, etc. So which syscall a program wanted, that it used to indicate by placing the index into this table in the register EAX. Okay. And arguments go in other registers as per convention. By the way, is this a concept which is known? I'm asking. So actually, when saying if you think of assembly language code, that when one function calls another, this is the convention. Like the arguments go in particular registers. Then there is a jump instruction to the called function, and that function also will put the return values in some designated registers, so that when control comes back to the calling function, the calling function will know where to find the return values. So this is how usually it is handled in assembly language. You push, the calling function pushes arguments into specific registers. Then there is a jump. The called function reads arguments from those specific registers. And again, the called function places return value in a particular register from where the calling function reads it. Is this known? Are you familiar with this? Okay, good. So yeah, so basically that is what we are discussing here. Fine, okay. Right, so yeah, in earlier days, syscalls used to be handled very similar to interrupts. Yeah. So if I just summarize it in one line, so earlier days, the kernel leveraged interrupts itself provided by the processors to handle system calls. However, this led to a problem later. So processor technology improved massively. So today processors are totally pipelined, and pipeline stalls, cache misses, these are very expensive. Right. So if there is a cache miss, then that leads to possibly a pipeline stall, and these can be very expensive because many other instructions will be delayed. So then the designers of processors started facing a problem. The problem is that the IDT is in memory. Remember what we discussed a few slides back? The IDT is in memory, and there is a IDTR register which holds the starting address, etc. So since IDT is in memory, it may not be in the cache. It may have been like replaced. That page may have been replaced. Who knows? And if so, the cache misses makes it very expensive because of this. Every instruction getting delayed due to pipelines, etc. So in modern processors, this is a problem which the designers started facing. That the IDT is in memory and it may not be in cache at certain point. Therefore, if there is an interrupt call and the IDT is, it leads to a cache miss. Okay. So the designers did something. This actually was first done by AMD, but the thing which I am going to tell you now, this technique was first adopted by AMD, but then AMD, I think you know that they are similar to Intel, they are another processor manufacturing company. So this technique, which we are going to tell you now, first was started by AMD, and it's proved really effective. Therefore, all other processor manufacturers also adopted it, and that is this. This is the technique. Store the IDT entry for a system call in a special CPU register. Okay. Store or cache the IDT entry for a system call into a special CPU register. So now, if there is a system call, you do not need to go to the IDT. There is a register itself within the CPU, which will tell you the starting point of the interrupt handler routine or whatever was stored in the IDT. Okay. So now you completely remove that memory access and you store the IDT entry for a system call in a special CPU register. But then this mechanism was made it very fast, but then there is a cost. Can you say what is the cost? This should be intuitive. Exactly, we need a register for a system call. So a large number of registers is required. Okay, large number of registers is required. Yeah, okay. Fixing the size of IDT is not a major problem because the set of interrupts given by or the set of system calls given by a processor is usually fixed. Right. So after manufacturing a processor, you cannot suddenly increase the number of interrupts. So usually that's not a problem. But the main cost is that a large number of registers are being needed to store the IDT entries. So my next question related. So when would you still go for it? Like there is a cost speed trade-off. I hope you understand that, a cost speed trade-off. So when would you still go for this? When would you still go for this mechanism that use a bunch of registers to hold the IDT entries? In what situation will you go for this solution? No. We are talking about standard processors. We are not talking about low power devices, etc. This is something that used to be done in like real computer systems, like full-fledged computer systems itself. I'm just asking in which scenario would you go for the extra cost? Okay, I mean, just a like intuitive answer. You go for a higher cost solution. Okay. So yeah, so Somai or Some anyway. So says, what's your pronunciation of your name? Some or Somai?
Hello?
Yeah.
Sir, it's Soumya.
Soumya. Okay.
Yes.
Okay, thanks. So Soumya says in case of limited number of syscalls. Why, Soumya? So.
Sir, maybe in case of more number of syscalls, the trade-off will be on the it will not be as much as helpful. But in case of if we have a limited number of syscalls,
Wait.
maybe
Limited number means you are saying the number of different system calls.
maybe we can already define a block of cache that will be used, and if the amount of system calls are more than that, then we can go for another method.
No, what do you mean amount of system calls? See, what I'm not understanding is, do you mean the total number of different system calls, or do you mean how frequently they are being called?
Sir, how frequently?
Okay, good. In that case, think about it. You said, and someone also supported it, in case of limited number of syscalls. So if the syscalls are not called too frequently, you will go for this approach. Okay, see, there are two opinions here. Soumya and someone else is saying in case of limited number of syscalls, and Pankaj and someone else is saying if the syscalls are being made very frequently. So there is these two opinions here. Which one do the others think? Yeah, basically what Somnath is also saying, you go for a higher cost solution only when you are sure that higher cost solution will actually save you a lot of time. Okay, and that is not only in operating system, it's through forever in life, in in our practical life also. You go for a higher cost solution only if you are sure that that higher cost solution will actually save you a lot of time, right? So suppose you have a like you have a cycle. Instead, you are thinking of going for a bike. There is no point in this extra investment unless you actually use that bike frequently. So that every day, maybe the cycling to your workplace took you 1 hour, by going by a bike will take you 20 minutes. But unless you do this every day, there is no point in going for the extra investment of going for a bike instead of a cycle. So exactly the same thing here. This solution of extra cost, extra registers makes sense only if system calls are so frequent that they are worth the extra transistor budget. Extra registers means extra transistors, right? So system calls should be so frequent that they would be worth the transistor budget. Okay. By the way, before going forward, let me just clarify. I have learned from that YouTube example. Here I used examples of cycles and bikes. They have nothing to do with interrupts. Okay. So please don't be confused. These are just analogies from real life. Okay. Coming back to operating systems and interrupts. Yeah. So I hope you get the idea that system calls should be frequent enough. Only then going for a higher cost solution makes sense. Right. And yeah, so there was another suggestion here, like Ishan said, dedicate a block of cache. Essentially, see, logically we are doing that, but system calls actually are so frequent that we are not even relying on our cache, we are relying on registers. So actually, there are a fixed number of system calls, but they are executed many times a second, hundreds of thousands of times a second maybe, or definitely at least 1,000 times a second. Therefore, we want to have the fastest solution. So it assigns some registers to hold the IDT entries. Okay. So AMD actually tried that out. Of course, that increased the cost, but then the speed of handling system calls became so fast that all other processor manufacturers also adopted this. Okay. So basically, now, just a minute. Okay. So now what happened is that now the concept of IDT is no longer there in IDT in memory. Rather, there is this, a dedicated set of cache holding the interrupt. Holding the system call starting points or system call handler addresses. And these new architectures started giving a special instruction for raising interrupts. So there is actually a new machine instruction which was developed essentially for raising a system call or asking for your processor to perform some task. It was hardware specific. Different manufacturers called it differently, like syscall, trap, SVC, etc. For x86-64 architecture, it is called syscall. And that name kind of, picked on because x86-64 architecture is in general the most common architecture. So that name picked on, like syscall. So what about this new instruction? So this syscall machine instruction takes operands, like say syscall 10. So this says we want this number signifies which system call we are making. Right? So this instruction use the machine specific registers that store the syscall entry point for every syscall. And argument, return values, etc. go in other registers as per convention. So that's the shift. Earlier system calls used to be handled similar to interrupts. Okay. But now there is this nowadays architectures usually give a special instruction and use these registers to store the starting point of system call handlers, or syscall handlers. Right. Okay, are these syscall registers writable? I don't think so. Like, it should not be allowed by application program to write into those. However, I must say that there are software configure. Okay, no, syscalls are not software configurable. That was in the era of interrupts. Yeah, some interrupts used to be software configurable, but I don't think syscalls are software configurable. Like, you cannot introduce a new syscall. You, as in the application developer, cannot introduce a new syscall. That is like the kernel has to do that. The kernel has to already give you that support. Otherwise, you cannot introduce a new syscall. Right. Okay. Now, so this was a bit lower level discussion as to how architectures handle syscalls. But when we write programs, then what do we mean by syscalls? So when we are writing programs in a high level language, typically say C, then we usually look at syscalls in a somewhere higher level context. Like, we do not want to keep track of which register to use and what number of syscall to call. Like, if I want an input operation, what syscall should I exactly do? What should be the number? We don't want to, remember all those things or burden ourselves with those. Therefore, the kernel or the operating system provides an interface to the services made available by these syscalls. And what are these services? Basically, so a syscall is a particular syscall executes hundreds of thousands of times per second. But the application programs do not see this level of detail. Things which were discussed actually, that see, one syscall, maybe there is a syscall for input. Then many different functions many different application programs may have actually asked for input. Right? So suppose your program has asked for input, but before it could be completed, your friend's program was allocated the CPU, and that program also asked for an input. Then someone else's program was allocated the CPU, that program also asked for inputs. So all these things can happen very fast, a number of times a second. But then you, as in the application developer, would not like to be burdened with all these details. So the OS understands that, and they basically provide an API kind of thing, where you can simply do function calls as if, and internally your library, etc., will handle or will make them or will translate them to syscalls. Right. So basically, the kernel gives us an application programming interface or an API. Things like fork, pipe, etc. Let us see one. Okay, before that, so when writing a program, we do not make that hardware function. We do not use that specific instruction called syscall, etc. We only have an API which will essentially give us some functions. And from your program, it will seem like you are doing just function calls. Now, since that is the most common way of using system calls, these APIs are also loosely termed as system calls. Right? Here is an example, the read system call. Okay. So understand that the kernel, the Linux kernel, does not give you fopen, fgetS, fprintf, etc., or printf, etc. Rather, the Linux kernel gives this API which has open, read, write, close, etc. So here is you can see read, the read system call. So see, I told you just a few minutes back about instructions called syscall, etc. Here you don't see anything like that because we are not talking about the architecture level, right? So the syscall instruction, then these registers, these are all at the architecture level. The kernel is hiding those details from us. And see, that is what we have been discussing right from the beginning of the course. The operating system is between the application program and the hardware and protects us from all the details of the hardware. Okay, so this is one system call like read. So here you can see, have any of you used read? I don't know. So basically read reads from a file descriptor. What is the file descriptor? This FD. And what are these two? Buff and count. What do you think? What are these two parameters? Buff and count. And it's very intuitive. Yeah, buff is the pointer to that memory location where it will store the data read. Right, so this system call needs to know where to store the data that it has read. So that is buff. And count is how many bytes to read. Okay, simple. So see, internally fscanf also possibly uses this. So you can so what you can do is see this. Let me show this picture. While writing a program in C, you can do calls like printf or scanf. These are not system calls. These are C standard library functions. So the standard C library kind of translates these calls to system calls, read, write, etc. However, this is just an API provided by the OS, right? Just as you saw the read function. So at the C library level also, you are not directly talking about syscall instruction. Somewhere lower down, the kernel calls the syscall instruction, where you possibly will use assembly language code and so on. Okay. So while writing C programs, you used to do printf, scanf. In this operating system course, we will ask you to do read, write. Right, but even this is an API. Even this is a kind of an abstraction which is given by the OS. The OS internally calls syscall, etc. But we don't have to deal about syscalls and registers and all. We will, in this course at least, we will keep to this level, like read, write, these syscalls we will use. Okay. Fine. So yeah, the next discussion would be different types of system calls. Again, we will discuss the APIs. Fine. So let me end today's class here. We will continue from here tomorrow. Any questions? Okay, fine then. So thanks everyone. Let's end the class. We'll continue tomorrow.